Um, the fall of 1988 was actually a quite eventful time for me. For one, I just started my master's program under Charlie Coburn. And that fall, I remember it was sometime in August that Charlie took me to Syracuse for a workshop. And after that workshop, I ended up in a hotel cafe where I met Doug for the first time. And I was just sitting there, eavesdropping on the conversation between Doug and Charlie, observing them work on what will become the paper on the pairwise balanced designs of block sizes 3 and 4. Now, curiously, although Doug and I had quite a number of common interests, I never had a joint paper with him. But my name would appear on that paper in the acknowledgement section. I think that's as close to a joint paper that I have with Doug. But later on, when I was doing my PhD, a third of my PhD thesis was actually inspired by Doug's work on frame-proof codes. So thank you, Doug, for that. So today I'm going to talk about something called cooling codes. It's in the intersection of designs, coding theory, and a little bit of computer science, and I hope Doug will like it. So some background. For integrated circuits design today, two of the most important criteria are actually low power and low temperature. Low power because of mobile applications, because of sustainability. Low temperature because, you know, when a circuit actually heats up or chip heats up, it actually affects a lot of things that's going on. It affects signal integrity. That means it's more prone to errors. Increases delay, so computations get slowed down. But there's also catastrophic failures. And all this come about because of aggressive technology scaling. Wires are getting longer and thinner. There's increased resistance. So it's not uncommon to have hotspots on a chip that exceeds 100 degrees Celsius. So this is an example of a catastrophic failure where you have a meltdown of the chip at temperatures too high. And on a chip, interestingly, the component that's impacted the most is actually the interconnects or the wires. So if you look at the diagram, the picture here, these are the interconnects, right? The wires that are connecting modules on a chip. And interconnects are actually the meeting point of all the modules because they have to communicate with each other, the modules, right? So they all meet at the interconnects. And why are interconnects getting hotter? Well, because there's increase in activity in the chips, computations are getting more and more complex. As mentioned earlier, feature size has also been reduced. Things are getting smaller and smaller on a chip. They're closer and closer together. And because they're getting closer and closer together, so there's actually insulation, this form of a low capacitance dielectric to prevent interference. But this material that prevents interference actually also locks in the temperature, the heat. So heat could not escape as efficiently. And the effects of this is that current leaks actually goes exponentially with temperature. And for every 20 degrees increase, you get 5 to 6% increase the delay of communication between modules. So minimizing the temperature on interconnects is actually very important. So how do interconnects get hot? I've mentioned why they get hot, but how do they get hot? Well, so this is a model that we'll use. That on chip, there are modules and they connect through a set of interconnects. And this setup is called a bus. Okay, in a series of papers between 2001 and 2006, by looking at the physical geometry, by looking at the electrical equivalent, and by looking at the thermal flow in these interconnects. Actually, what's surprising is that the power and the temperature of a bus can actually be quite simply described as being determined by its switching activity. I'm going to tell you what switching activity means. So an interconnect is in one of two states. Okay, so a wire is in one of two states. Either it carries a 0 or 1. And a switching occurs or a transition occurs where the wire or interconnect changes state. So as an example, there are two modules connected by 6 interconnects. So at time t, suppose the 6 interconnects are in their states that are described, that are shown in the picture. And at time t plus 1, we wanted to communicate another state, 011,001, and we set that across. So there's a total of 3 transitions here, right? Shown by the numbers in red. Okay, from time t to time t plus 1, there are 3 transitions. So there's a total switching activity of 3 on the bus. And when an interconnect changes state, it actually heats up. Okay, so the wire with a corresponding red number are those interconnects that gets heated up when the transition takes place. When a wire has no transition, it actually maintains the temperature. So how do we cool, how do we actually communicate in such a way that we don't want to heat up the bus too much, right? So before I describe the codes, let me go through a few preliminary setup. So a bus will comprise of n interconnects and a vector of n states. So one state corresponding to a state of one interconnect that's transmitted on a bus will be called a code word. Okay, so a code word will be an n-dimensional vector, a binary vector. And the set of all code words is called a code. So there are 2 key features of a coding scheme where it relates to communication on a chip. The first is what we call property A. So property A is parameterized by a parameter t. And every code word, and the code is said to have property AT if every code word avoids state transitions on the T hottest wires. Okay. So property AT is what we need to regulate the peak temperature of a bus. Okay. And I'll call a code an anti-cooling code if it has property AT. The second property is what is called property BW. A code has property BW if every code word causes state transitions on at most W interconnects. Okay, so this regulates the power of a bus. So remember, the power of a bus is determined by the total switching activity, the total number of transitions on that bus. Okay, and I'll call a code an NW low power code if it has property BW. So the previous, quite a number of previous work on low power codes. Stan and Burleson in '95 had described what is called bus invert coding. The idea is very simple. So if a code word X causes more than half n of transitions, it just send the complement instead. Okay, but the receiver needs to know whether the original vector was sent or the complement was sent. So there's an additional interconnect that's needed to actually signal that whether it was the original code word that was sent or its complement. Okay, so there's a redundancy of 1. So this is it's easy to see that this is an n/2 low power code, and because the total number of transitions is never going to be more than n/2. Then in a joint work with Charlie and Alan Ling in 2006, we observed that any two code words cause at most W transitions if and only if the Hamming distance between them is at most W. This is quite obvious. But what's interesting is that this question was asked actually by Adish back in 1961 in its set system equivalent. And that problem was completely solved by Kleitman in 66. So with this observation, we actually have optimal NW low power codes for every N and W. So not just when W is N over 2. And these codes have size big data of N to the W over 2 for fixed W. And on the temperature side of things, Wang et al. In 2006 suggested a thermal spreading approach. So the idea is that to have a code where transitions with respect to any position or any of the interconnects is equally likely to happen. So if you look at a large ensemble of communications, the temperature profile of the interconnects is going to be quite flat. Okay, and then between 2007 and 2010, I noticed that thermal spreading is just a requirement of equireplication, right, on the codes. So I gave a number of talks during those years on constructions for a few versions of thermal spreading codes. But I was never quite satisfied. I never published them because there's actually a bigger problem here that's unsolved. And the bigger problem is that thermal spreading isn't quite what we are looking for. Because although it flattens the temperature profile of the interconnects or the bus, that temperature profile could be rising. Okay, because it just spreads the transitions around, but it doesn't really try to cool anything. Okay. So what is more important is that we want to control the peak temperature. We don't want any of the interconnects to get too hot, because once they exceed a certain threshold, they melt out. Okay. So what we wanted to do is to control the peak temperature by avoiding transitions on the hottest wires until they cool down sufficiently, and then perhaps we can use those interconnects, the transitions for communications again. So this was what motivated property AT that I've seen earlier. They wanted to avoid transitions on the T hottest wires. And there are no previous work. There were no previous work on codes deliberately designed to lower peak temperature. Why is that? Maybe it's not even possible. And indeed, it's not possible. Okay, it's not possible to satisfy the property AT even when T equals 1. Why? Well, suppose you want to avoid transition on interconnect I, which is the hottest interconnect. To guarantee that there's no transition, that means you need to have a 0 on position I of the code word. But you don't know what, but any one of the interconnects could be the hottest interconnect. Right. So in other words, so not 0, but you need the position I to be of the same state as the previous transmission. But that means that the code word that you're going to send has got to be identical to the code word that I sent before, in order to guarantee that you do not make any transition on the hottest wire. So no communication is possible. Right. And so I stopped working on this for a while. And I mentioned this problem to Alex Vardy, who suggested that we look at using differential encoding instead to communicate a code word, not directly transmitting the code word, but actually transmitting the code word in the difference between what you want to send and what was sent before. And this was actually quite useful. So let me give an example of what differential encoding means. So suppose we have the two modules communicating. Let's say at time t that we want to set the code word 001010. So that code word is sent across the bus. And that code word is also stored in a buffer. Okay, so after the sender sends the code word, it stores it in its buffer. And when the receiver receives the code word, it stores it in the buffer. Say at time t+1, we want to set the code word y, 100010. What we do is not to send y directly, but to send the difference of x and y. Okay, so instead of transmitting x, instead of transmitting y, we send x minus y, or x plus y, since we are in a field. So the difference between x and y is 101000, and we send that across instead. And once the sender sends that difference across, it updates its buffer with what it has just sent across. And when the receiver receives the difference, what it needs to do to recover the code word is just to add what's in the buffer to it. Okay. And then after decoding, it stores what it receives in the buffer. And that's ready for the next round of communications again. So there's something useful about differential encoding in that when we use differential encoding to transmit a code word, say X, there's actually a state transition on an interconnect if and only if there's a position that the corresponding position in the code word is a 1. Because when you take the difference, if there are no transitions, that means the two of them are identical, right? So there's a 1 in the code word, means that you're actually flipping the bit from before. Okay, so if it's a 0, there's no flipping, so there's no transition. So there's a transition if and only if the corresponding position has a 1 in the code word. And the total number of transitions is just simply the Hamming weight of the code word. So with this, let's revisit low power codes again. So recall property BW, that every code word calls state transitions on at most W interconnects. And without differential encoding, we have seen that a code satisfies property BW if and only if the Hamming distance between any two code words is at most W. Right, we've seen that before. So that was the solution is actually Kleitman's solution, right? It's Kleitman's theorem. But with differential coding, a code satisfies property BW if and only if every code word has weight at most W. This means that if we use differential encoding, the optimal code that we're going to have, the largest code, is just simply the set of all vectors of weight at most W. Yeah, and that has size data n over W. So this solution is actually extremely simple without appealing to Kleitman's theorem. And it has size much larger than the data of n to the W over 2 that we have constructed earlier. So what do we give up? A buffer. So previously, there's no need for a buffer. The optimal code we have is n to the W over 2. With a buffer, we get n to the W. But the code is a lot simpler to construct. So with differential encoding, I went back to look at the cooling codes again, codes that cool interconnects. I recall property AT means that every code has to avoid state transitions on the hottest interconnects. And under differential encoding, now property AT becomes means that for all code words X and for all S, so S is the index set of the T hottest wires. We must have X, when restricted to those positions in S, be the zero vector, because it must not cause transitions on those T hottest wires. But if you notice, still no communication is possible, because this means that every of the coordinates has got to be zero. So we need one more idea. That's the idea of a code set. So in a code, it's basically a set of vectors. But we want to now look at the code as a set of vectors. Okay, so they are pairwise disjoint. So let me give you an example. It'll be easier to see. Excuse me. So now C is a collection of sets of vectors. And each of these sets will be called a code set. Okay, if you look at the, so each row here is actually a code set. If you look at all the code sets, they are pairwise disjoint. So no vector appears in more than one of them. And how do you use a code set to communicate? Well, each message corresponds to a code set. Okay, so if you want to send a message, you first look up the corresponding code set and pick one of the vectors inside, or one of the code words inside, and use that as code word and transmit. Okay, the pairwise disjointness of the code set guarantees unique decoding. So when a receiver receives a code word, there's only one code set that can contain that code word because they're pairwise disjoint, and that will be the corresponding message. So using this method of communication, now a code satisfies property AT if and only if for all code sets and for all set S, which is the indices of T hottest wires, there exists some code word in that code set. When restricted to S, gives you the zero vector. Okay, so because of this, now there can exist such a vector that's non-zero. So as an example, this is actually a 6.2 cooling code. What this means is that if you pick any code set, any row, so which means for any message, and for any two hottest wires that you want to avoid transitions on, I can actually find a vector in that row that you have chosen that's got zeros in those two positions. They'll precisely avoid transitions on the two hottest wires. So let's say you pick the second row. Let's say you want to avoid the two hottest wires, which are the first and the last. Well, the first code word will do it. Okay. And in fact, for any of these rows, any two indices you pick, you can always find such a code word. So now the construction of cooling codes becomes possible. And one easy construction is wire spreads. I apologize tomorrow for appealing to geometry. But a spread would actually give you a cooling code now. Okay, so a spread is basically a partition of the, in this case, a binary space, vector space, into subspaces of a constant dimension. And if you look at, so it's not quite pairwise disjoint, right? Because every one of these subspaces actually contains the zero vector, right? But if you were to remove the zero vector, then they become pairwise disjoint. And you can take each of these class as a code set. And it's quite easy to verify with linear algebra that, in fact, this is a cooling code. These are n. Okay, so if you pick the subspaces to be of dimension t plus 1, then this gives you actually a NT cooling code. As long as t plus 1 is at most n over 2. And their size to the n minus t minus 1. And this is optimal in terms of redundancy, because we can show that any code that needs to avoid the t-Hortus wires, you always need t plus 1 wires as redundancy. What about low power cooling codes? So these are codes satisfying both properties AT and BW. And if you were to consider a Baranai partition, so Baranai partitions are, you can see it as a one factorization of the complete K uniform set system, or you can see it as a large set of one designs. And Baranai partitions are actually also cooling codes. And they are cooling codes when t plus 1 is less or equal to n over w. And Baranai partitions are not just cooling codes, but because they are W uniform, they are also actually low power codes. So they are both low power as well as cooling. Cooling codes are connected to other codes. They are connected to write-once memories. In cooling codes, you need the restriction to S to be 0, the 0 vector. But for write-once memories, you need them to be with the all-ones vector. In the cooling codes case, you are restricting S to be a subset of size at most T, because t-Hortus wires, but S is unrestricted in the case of write-once memories. And cooling codes have been used to construct worm codes. It has also been used to code for stuck-at faults. In this case, you need the restriction to be any vector, any specified vector, so not just 0 or 1. And cooling codes here actually requires much less redundancy compared to the usual constructions out there. And there are obviously many interesting combinatorial problems arising from cooling codes and low power codes. But one that's particularly interesting is re-asking an old question in design theory. Because of the applications of Baranai partitions now, we actually wanted explicit constructions and fast algorithms for Baranai partitions, because this is useful for encoding and fast encoding and decoding. And explicit solutions for k equals 2 is known since the 19th century. This is just one factorization of the complete graph. For k equals 3, solution was obtained by Pelterson in 1936. For k equals 4, a solution was claimed by Beaumont in the 70s, but was never published. We wrote to him. He could not recover the construction anymore. And it's quite unlikely that that it also covers all the classes of all the congruence classes of n. So with Tuvi and Chengmin and Alex and Hamao, we decided to actually try to come up with an explicit construction from scratch. And we managed to obtain one quite recently. But it was very technical and really very tedious. So an open question would be, is there a more general way of doing it for higher K? Okay, so I'll end with this, and I'd like to wish Doug a happy 66. Thank you.